All right, Chem Gang, now that you know the basics about radioactive decay and you've seen some graphs and models of this exponential decay, let's see how you would handle problems using these ideas. So what I've done is I've set up a chart here, and you don't have to set up this full chart for every problem, but you might sort of envision elements of it, and if you're kind of showing your work, you would pick certain parts of the chart, depending on what your problem is, to write down and kind of sketch out. And so the way the chart works is we're going to always assume that there's uh, a whole number of half-lives passed. To do problems without that, you would need more advanced math that we don't know. So this is a good starting point for us. And what we're going to do is mainly we're going to determine how much of the sample is left. And the idea is every time a half-life passes, we cut the sample in half. So I'm going to start with a fraction because that's, I think, the easiest thing to think of. You start with the whole sample, a whole, and after one half-life, that's cut in half. So you have half the sample. Oops, I think we got to reformat that. So let's just go to text. All right, and back up one half. All right, much better. And let's align that. Uh-oh. All right. So that's after one half-life goes by. If a second half-life goes by, that gets cut in half again. And again, we saw this on the simulation, usually with the percents and the pi graphs. So a third half-life will cut it in half again. So you see how it goes. I can keep filling out this column. Oops. Keep filling out this column by cutting in half each time. So this is an easy way to determine the fraction of the original sample that will remain. As a percent, we're doing the same thing, except we're cutting in half as a percent. So after one half-life, 100% goes to 50. And then after another one to 25%, et cetera, et cetera, et cetera. So I just keep cutting in half. There's some rounding going on here. We can fix that later. 65.0325. Okay. And again, this is rounded a little bit. I can make it look a little bit better by adding a decimal place or two. So now you see there's not as much rounding as you thought before. Okay. All right, so that's sort of the basics behind it. These last two columns here, the time passed, you would have to know something about the half-life. You have to know how long the half-life is. And in many problems, that information is given to you. So I'm just picking a random number here. I'm going to say the half-life is 13 minutes. That means one half-life means 13 minutes has gone by. All right. And each half-life that goes by is another 13 minutes. So I can just keep adding on 13 minutes each time. So after another 13 minutes, that's two half-lives, is 26. Three half-lives is another 13 minutes, oops, which makes a total of 39 minutes. Okay. And then 52 minutes. Again, I just keep adding 13 minutes each time. Okay. And of course, I hope that you're seeing that not only are we adding 13 minutes each time, but you're really multiplying. So after three half-lives, you multiply 3 by 13 minutes, and you get 39 minutes that go by. And that's an easier way to find out the time at the end. If you don't need all these times, you can just say, all right, 6 half-lives went by times 13 minutes, that's 78 minutes. Right? For the amount of the sample present, you have to know how much was there to start. And it might be given as a number of atoms, or it might be given as a mass. So I'm going to just pick 20 grams as the amount of sample that's there to begin with. And it's the same deal as before. It's really pretty simple once you get the idea of the graph. Every time a half-life goes by, you cut that in half. So after the first half-life of 13 minutes, you got 10 grams. And then after another 13 minutes goes by, you're down to 5 grams. And again, just keep cutting it in half each time. And you get the idea. There are kind of shortcuts to this too, because if you take the 20 grams that you started with and you multiply it by 1/64th, that's what you'll get. Or if you take the 20 grams and multiply it by 1.56%, that's what you get. So, you can step through, but if you know these numbers here, you don't have to determine the mass at every step of the way. So that's kind of how the chart works out. Let's actually pick some problems and show how we might work them out. So here's a simple problem we might approach. It asks us what fraction of a sample remains after 5 half-lives pass. And what I'm doing is I'm defining a symbol here. This arrow means a half-life is going to pass. So this is going to be an easy way, without me having to explain in a lot of words what's going on in the problem. And I'm going to need 5 half-lives passing, so I'm going to make 5 arrows. Okay, and this is before a half-life pass at the start. I would have, okay, 1 or the whole sample. It asks what sample remains. Okay, after the first half-life pass, I have to cut that in half, so I have a half left. Okay, and after another one, I cut that in half, so I have a fourth left. And you see how I'm doing the problem here. And it's really kind of, all laid out for me. I'm going to cut it in half again, and cut it in half again, and cut it in half again. And again, if I wanted to count the half-lives that have gone by, that's the first one, the first arrow, there's the second arrow, there's the third arrow, there's the fourth arrow. I already counted them out before, so I know this will be right, and there's the fifth arrow. So I'm kind of counting the half-lives that go by, and I show the fraction that remains each time. All right, so how do these get a little bit harder? So let's look at another way that we might pose the same problem. So instead of telling you that 5 half-lives pass, you might see the problem look like this. So it turns out this is really the same problem here, but it's written differently. So it first tells you that your sample has a half-life of 6 minutes, then asks how much remains after 30 minutes. And what you should be seeing here is that means 5 half-lives have passed by. In other words, 30 minutes that have passed divided by 6 minutes per half-life, okay, equals 5 half-lives left. And quite honestly, you can show this as a conversion. If I were to kind of clean this up, I'm going to have to reformat this a little bit. That's divided by. So what I'm really doing is multiply by 1 half-life over 6 minutes. Okay, so I'm going to underline that there, and then put this down here. Oops. And the line spacing is going to be messed up there, but if I can remove the space after this, it'll look nice and tidy. Okay, so this is using the conversion method to do the same thing. You can sort of do it in your head because it's easy math. But 6 minutes have passed. I'm going to get rid of the minutes and cross it out with the minutes down here. Again, that's how you set up a conversion. And again, what we wanted to know is how many half-lives passed. So right here it says 1 half-life is 6 minutes. Right? So this turns out to be 5 half-lives. Okay? And once you've got that, then you just do the problem exactly like you did before. You make 5 half-lives passed. Okay? Another way to do it, which doesn't quite show as much understanding, but will get you to the same answer, is instead of counting the half-lives that go by, just keep counting minutes. Okay, so when you start out, you're at 0 minutes. Okay, we need to get up to 30 minutes. So that first arrow represents 6 minutes. Okay, and actually I'm gonna leave the unit out because it's, whoops, because it's gonna be too crowded here. But that next arrow is another 6 minutes, which is 12 minutes. And the third arrow is another 6 minutes, which is 18, and then 24. And then the last arrow is another 6 minutes, which means 30 minutes. So this is the arrow that represents 30 minutes have gone by, and you're down to 1/32 of the sample. Okay. The last thing that you might have is an amount. So it might say a 2,000 atom sample has a half-life of 6 minutes. Okay. How many atoms remain? Whoops. After 30 minutes. Okay. And there are a couple approaches to this. So the first thing you would do is find the 5 half-lives. Okay. And then you can look at the fraction and say, well, 1/32 is going to remain. And then just say it's 1/32, okay, times 2,000 atoms. Okay. That's essentially the fraction that remains. So, whatever that comes out to, it's going to come out to, I think, about 60 atoms or something like that. All right. The other way you could do it, though, is you can cut your sample in half each half-life. So once you know that it's 5 half-lives, I'm not going to write it down again, you just write that you have 2,000 atoms to start. And I'm going to have to spread this out a little bit just so we can see it a little bit better. All right, but after this first half-life here, okay, you're going to cut that in half, and there'll be 1,000 atoms, okay, which represents a half of the sample. In another half-life, it'll be down to 500, which is a quarter of the sample. In another half-life, 250, which is an eighth of the sample. And then 125, which is a 16th. And again, I just keep cutting in half. And 62 and a half. So it means you'll have about 62 or 63 atoms if it's following it exactly. Okay, can't have half of an atom there, but you get the idea. And like I estimated before, that's about 60 for your answer. So that's the first type of problem. There is one other type of problem that asks you to find the half-life. So let me type that out, and then we'll try to handle that. All right, so here's the other type of problem, which is going to ask us what the half-life is. And typically, it will tell us how much the sample has been reduced and how much time it's going to take. So we can think of this, we can think of it in terms of a conversion. We want to know what 1 half-life is. Okay, and we're essentially going to multiply that by, again, there will be a conversion ratio, but down here we need to know how many half-lives have gone by. Oops, gotta put it down here. And again, half-life is up there. We have to have half-lives down here. Whoops, can't type. And again, these are going to cancel out, so we can strike them through. Okay, and this up here is the 48 hours, because the half-life, remember, is a time. We're looking for a time, and that should be underlined, so we'll underline that there. Okay, so this is the setup here. It's basically 48 hours divided by the number of half-lives that have gone by. So you're splitting this 48 hours into a certain number of half-lives, 1 or 2 or 3 or something like that. And this is how it's shown as a conversion. So what we really need to do is figure out how many half-lives went by in that 48 hours. And that's pretty simple if we take the amounts here and we just kind of reduce them. So you have, oops, 40 grams here. That shouldn't be strike through. Let me get rid of that strike through. Okay. After a half-life goes by, and I'm just going to put my half-life symbols here. Whoops. And again, I'm just putting a bunch of them. I don't know how many we're going to need, but we have to reduce 40 grams to 5 grams. So the first half-life is going to reduce it to 20 grams. The second half-life is going to reduce it to 10 grams. And the third half-life is going to reduce it to 5 grams. Well, we've made it. Okay, we don't need these additional half-lives. But we can kind of count here and see we've had, whoops, 1, 2, 3 half-lives go by. So that 48 hours is essentially split into 3 half-lives. Okay, and since that's a 1 to start with, we see that our answer is 16 hours per half-life. Okay, 48 divided by 3. Right. So that's an easy way to do it. You can also do this by fraction. You can see that 5 out of 40 is 1/8. And again, we kind of showed that up here. It takes 1, 2, 3 half-lives to reduce a whole to 1/8. So that's how you do the problems. Good luck on the ones on the worksheet, and hope you enjoyed this video.